Hello, and welcome to my presentation on the use of Mahalanobis distance for outer-distribution detection. To introduce myself, hello, my name is Harry Anthony, and I'm a PhD student at the University of Oxford. Previously, I got a Master's in Physics at Imperial College London, and now I'm studying for a PhD under the supervision of Professor Kamnitsas. When training a neural network, we use a set of training images given by the symbol X and corresponding labels given by the symbol Y, which we call the training data. We can then use this to train a neural network, given by the symbol F, for a task such as classifying diseases from an X-ray scan. Once the model is trained, it can be applied to images without labels during inference. Most of these images belong to the same distribution as the training data, referred to as in distribution. However, the model may encounter images that differ significantly from the training data, known as out of distribution. When a pre-trained neural network encounters an out of distribution input, it has been observed that this can cause the networks to give erroneous predictions. This is particularly concerning in medical applications, as such errors could have serious consequences for clinical decisions downstream. Therefore, we want to develop methods for detecting when an input differs significantly from the training data, known as out-of-distribution detection. Out-of-distribution detection can be thought of as developing a scoring function S, which is dependent on the input image X and the neural network F. If we plotted a scoring function, we would want to see all the out-of-distribution images, given in orange, separate from the in-distribution images, given in blue. Such a scoring function could be used to place a threshold, given by the symbol tau, where we say everything below that threshold is out-of-distribution, and everything above that threshold is in distribution. Out-of-distribution methods can be put into two categories: internal methods that use outputs or parameters trained on the task of interest, and external methods which are external to the original model. We separate the internal methods into two further groups: ad hoc methods, which require a type of network architecture or for models to be trained in a given way, and post hoc methods, which can be applied to pre-trained networks. There are several benefits to post hoc methods. The first is it can be applied to pre-trained neural networks. There's no requirement to retrain them. Secondly, they usually work with most model architectures, so it's not dependent on the type of model. And finally, it's a low computational cost typically. And one of these post hoc methods we're going to explore today is called the Mahalanobis score. This method is quite well used because it's quite intuitive. However, its performance in the literature is sort of mixed. It does well in some studies and less well in others. So this suggests we should study the best practices for this method. So let's run through this method. Here we have our neural network, which has already been pre-trained, and we're giving it a new input. Somewhere in this network, we can extract embeddings using a feature extractor and collect the following feature maps. The mean of these feature maps can then be used to define a new embedding vector. We can study where the training data lies in the latent space of the neural network. We can then compare this to where the in-distribution and out-of-distribution inputs appear in the latent space. We can hypothesize that the in-distribution data will be closer to the training data in the latent space compared to the out-of-distribution data. Hence, by measuring the distance of an input to the training data in the latent space, we can test for out-of-distribution inputs. It may be intuitive to measure the distance using Euclidean distance from the input to the mean of the training data embeddings, where mu here represents the mean of the training data. However, the Euclidean distance does not take into account the correlation between the variables. So in our example here, it would not be able to separate the in-distribution and out-of-distribution inputs. Therefore, we often opt for the Mahalanobis distance instead, which takes into account the correlation between variables. Mahalanobis distance is equivalent to the Euclidean distance, apart from we divide by the covariance matrix, which is given by large sigma. This measures how variables covary with each other. This is equivalent to fitting a Gaussian distribution to the training data under a maximum likelihood estimator. However, in reality, the training data will contain several classes, which we expect to occupy different regions in the latent space. To account for this, we measure the mean and covariance matrix of each class in the training data. We then use this to measure the Mahalanobis distance to each class centroid in the training data to our test input. Finally, the distance to the closest class centroid is called the Mahalanobis score, and we use this as our out-of-distribution scoring function. To study this method, we use the CheXpert dataset, which is a set of multi-label chest X-rays. For our training data, we got images either with positive cardiomegaly or positive pneumothorax, and we trained a neural network to classify between these images. We then used 10% of unseen images as our ID test cases. And our out-of-distribution test cases, we added a synthetic grey box to each of our ID test cases. The reason we use the synthetic artifacts is because it gives us a lot of control to see how these artifacts impact the results. First, I looked at the case where the grey square took up 10% of the pixels of the image. I then extracted the embeddings after a module and used Mahalanobis score to calculate the area under the ROC curve. This was then repeated for all the modules in the network. Looking at the results, we can see a pattern that the detectability of the synthetic artifact reduces through the depth of the network. Here, the grey dotted lines represent downsampling operations in the network. This experiment was then repeated for boxes of size of 7.5%. and boxes of size 5%. Here we see, maybe intuitively, that smaller artifacts are less detectable throughout the modules of the network. Moreover, if we zoom into the results, we see a trend that the AUC typically improves after a ReLU operation, which is highlighted in green, compared to its preceding convolution and batch normalization operations. The most common implementation of a Mahalanobis score is to apply the feature extractor on the last hidden layer of a neural network, as shown here. However, when looking at our results, we see that applying the Mahalanobis score on the last hidden layer is actually one of the worst possible AUC scores in the whole of the network, which again is the most common place to apply the Mahalanobis score. We hypothesize that the performance of this suboptimal configuration may be diverting the community's attention away from the potential of distance-based out-of-distribution detection methods. We then repeated this investigation with another synthetic artifact. In this case, it was a white ring artifact. The results of this experiment are shown here, with the results for the ring artifact shown in orange and the square artifact shown in purple. We found this result really interesting, how the trends of these artifacts for the same pre-trained network are very different. The square artifact is detectable earlier in the network, where the ring is detectable later on in the network. From this result, we clearly see that different artifacts are optimally detected at different parts of the network, and trying to find a single module in the network which can optimally detect all artifacts may be misguided. Another common implementation of Mahalanobis score is collecting the distances after the residual blocks in a network, and then weighting them together to get one single score to use for out-of-distribution detection. The distances are weighted by coefficients alpha, which are typically found by using logistic regression on an out-of-distribution dataset. So we applied this method on our results, with the layers used for weighted combination shown in blue. The optimized weightings for each pattern, calculated using logistic regression, are then shown on the right. Here we see the ideal weighting for one artifact actually causes a degradation in performance for the other. Hence, there is no single weighting that optimally detects both patterns. As these type of out-of-distribution patterns that can be encountered are very unpredictable and vary greatly, the idea of searching for an optimal weighting of layers may be ill-advised. So, some of the key takeaways from our synthetic artifact experiments are: application on the last hidden layer of a network can actually be very suboptimal, despite being the most common implementation of the method. Moreover, the performance of this method typically improves after an activation function, like a ReLU, and different types of out-of-distribution artifacts are optimally detectable at different depths of the network. There is no one-fits-all depth. This final point motivates us to think that out-of-distribution detection may be improved by using multiple OOD detectors, each at different depths of the network, trying to identify different artifacts. To investigate this, we created a method which uses multiple detectors, which we are calling multi-branch Mahalanobis. How this works is we divide the network into parts, separated by downsampling operations. We refer to each part as a branch. The Mahalanobis distances after all the modules in the branch are then collected, and they're combined to give us a single score. This score is the sum of the standardized distances in the branch, using the mean and standard deviation of the distances in the training data in the branch, in order to prevent a single module in the sum dominating. This was then repeated for the following branches in the network, such as that we have a score for each branch acting as its own out-of-distribution detector, allowing us to have multiple detectors in the network. For example, in a Resonant 18 architecture, we have 4 detectors. Moreover, we wanted to validate our findings on a real-world out-of-distribution task. However, most out-of-distribution medical image tasks have heterogeneous artifacts, which complicates analysis of patterns. Therefore, we decided to create a clean and reliable out-of-distribution evaluation benchmark for medical imaging. We manually annotated approximately 50% of the frontal X-rays in the CheXpert dataset, creating a class of images with no support devices that can be used as an in-distribution set, and a class for pacemaker devices, which contain a visually distinct image pattern and can be used as your out-of-distribution test set, enabling analyses of the performance of out-of-distribution detection methods on a real artifact. As a contribution to this work, we are making these manual annotations publicly available, which can be accessed to my GitHub, and we hope this will be useful for the community for assessing out-of-distribution methods in the future. We then use these manual annotations in the following way. First, we trained a model to classify between images with pleural effusion and without pleural effusion, where all images had no support devices. We then used 5-fold cross-validation for our unseen ID test cases, and we used images with pacemaker devices as our out-of-distribution test cases. For our second task, we trained a model on the same pleural effusion task, but only using scans of male patients with no support devices. Using 5-fold cross-validation for our ID test cases, we then used female patients with no support devices as our out-of-distribution test set. Firstly, here is the AUC for Mahalanobis score for the unseen sex task across the modules of Resonant 18, similar to our analysis on the synthetic tasks. The branches used for multi-branch Mahalanobis are shown with the grey brackets. Here we see that this out-of-distribution task is most detectable in the middle of the network, at branch 3. Now if we look at the unseen pacemaker task over Resonant 18, we see that this pattern is most detectable at the end of the network in branch 4. Here we validate some of our findings on the synthetic artifacts, that different types of out-of-distribution patterns are more detectable at different depths of the network. Now we can compare results on the pacemaker task to our other post-hoc out-of-distribution detection benchmarks. I won't go through each method individually due to time constraints, but here we have maximum class probability, which is the baseline. However, it does not perform very well, it's only 58%. We see similar results for Monte Carlo dropout and deep ensembles, where in the latter we use 3 seeds per k-fold. We do see a notable improvement with OOD. However, those who are familiar with this method know it has 2 hyperparameters which can be configured in an out-of-distribution dataset. However, in real-world deployment, it is impossible to configure these parameters for all unseen out-of-distribution tasks, so we are unlikely to get the full potential of this method during deployment. So we've marked this method to highlight this. Now let's look at Mahalanobis score applied on the last in layer of the network. We see that this method performs quite poorly. It actually performs worse than the baseline in maximum class probability. As this is the most common method for applying Mahalanobis score, this may be misguiding the community from its full potential. For example, if we apply this on the best layer of the network, we get a huge improvement in out-of-distribution detection. However, it's not possible to know what the best layer to apply Mahalanobis score is for an unknown out-of-distribution artifact ahead of time. So this performance is unattainable. However, if we use a weighted combination, the layers of weighted combination, we do get an improvement. Here we've used an equal weighting for the layers from our discussion earlier about weighting layers being misguided. Moreover, a contribution of mine is to remove the last in layer from this weighted sum, and we see that this improves the performance even more. Now let's compare these scores to our multi-branch Mahalanobis method. Here we've plotted the AUC for each branch in the network, and we see that the last branch in the network performs very well, at 76%, and it actually has a better performance than the best individual layer of the network. This highlights the utility of combining distances to get a single score, and it reduces the degrees of freedom of trying to find the best single layer in the network. However, we can do even better than this. If you recall earlier, we showed that the performance improves after a ReLU operation. And so by just using the ReLU modules in the branches for our multi-branch Mahalanobis, we get an even better improvement on our score, where I've highlighted that in green. But we can do even better than this. A method called fast gradient sign method can be used to improve this performance by first backpropagating using the Mahalanobis distance as the loss. This can then be used to calculate the perturbations, which can be added to the original image to reduce the Mahalanobis distance. We then multiply this by a scalar hyperparameter, epsilon, to get a perturbed image. It has been shown empirically that the rate of change in Mahalanobis score for the perturbed image is greater for in-distribution than out-of-distribution images, which improves their separability. And we can see that applying fast gradient sign method gives us a further improvement on our last 2 branches. However, these are again highlighted because they have a hyperparameter which has to be configured, so the whole benefit of this method may not be attainable in a real-world deployment. This analysis was then repeated with our male versus female out-of-distribution task, and we saw the same trends that we did with our pacemaker task. However, I'd like to bring your attention to the multi-branch Mahalanobis results, as we see here that the third branch actually performs better than the fourth branch in this case. This reconfirms our idea that using multiple out-of-distribution detectors may be required to detect different patterns more optimally. These were repeated with the VGG model, however, I'm not going to show them today because of time constraints, so check out our paper if you want to see that. So finally, I would like to discuss the application of multi-detector systems. We saw just then that multiple out-of-distribution detectors can improve performance over single detectors. However, can they be used in real-world deployment? With a single detector system, we develop a single scoring function where we can find a single threshold for separating ID and OOD inputs. However, with a multiple detector system, we now have many scoring functions, and this creates an additional challenge of trying to find multiple thresholds for each detector, which are complementary for each other. To study the feasibility of finding these thresholds, we apply a grid search on the 4 detectors of multi-branch Mahalanobis. We then configure these thresholds such that if one flags an input is out of distribution, it is then marked as such. These thresholds were optimized using a balanced accuracy metric over the whole dataset of both the unseen CheX and the unseen pacemaker task. We compare the results to the best performing single detector systems from our previous analyses on ResNet 18. We see that the theoretically attainable upper bound for multi-branch Mahalanobis outperforms both the optimized single layer and weighted combination techniques. This shows that our thresholds can be found to accommodate multiple out-of-distribution tasks, and so methods for configuring such multi-detector systems can be an avenue for future research. So finally, to summarize the key takeaways from this talk, where you apply Mahalanobis distance matters. Measuring at the final layer of the network is very suboptimal, despite being the most common practice in previous works. Moreover, measuring Mahalanobis score after a ReLU operation generally improves the detection. We also saw that different out-of-distribution patterns are optimally detectable at different depths of the network. There is no ideal layer or combination of layers that can optimally detect all patterns. We saw that the sum of distances at different layers can actually outperform the best single layer of the network in some cases. And finally, we saw that multi-detector systems can be used to improve the detection of different outer distribution patterns, motivating the design and calibration of such systems to improve outer distribution detection. Thank you for listening.